Hello and welcome to the fifth lecture within my recorded series. It corresponds to the last little bit of my Wednesday lecture first week, and Thursday lecture from first week, and then starts into what we'll cover Monday of second week. So we're going to cover intermolecular forces, look particularly at solubility. Intermolecular forces eventually will affect physical properties, which I'll break into the last and final chapter 1 section. But for now, go ahead and get rolling on intermolecular forces. And so intermolecular forces deal with any interaction between two molecules that is not a covalent bond, holding them all together, at least in organic chemistry. And technically, I guess, in a solid, ionic bonds are considered ionic interactions. So we don't really call them intermolecular forces because they're not molecules, but still a charge interaction. So what we're talking specifically is molecules, things held together by covalent bonds, have the internal bonds we talked about, Honk rule, carbon makes 4, hydrogen makes 1, nitrogen makes 3, oxygen makes 2. Those are covalent bonds holding the molecule together. But between two molecules can exist a weak force, a medium force, a strong force, not as strong as covalent bonds, but forces that have some value, if you will. And so I want to first start by defining them, and then ultimately we're going to figure out how they impact first organic chemistry and then a little bit of biochemistry or physiological chemistry. So dipole-dipole interaction, as the name implies, is interaction of two dipoles. Typically, it's a delta plus attracted to a delta minus. The stronger the force between them, the more tightly the molecules will be held together. And then that force depends on the magnitude of the delta plus, the magnitude of the delta minus. But technically, it also means a delta minus interacting with delta minus or delta plus with delta plus, which causes molecules to move away from one another, to repel from one another, rotate, twist, turn, but they'll eventually move into a position where the optimal scenario is pluses next to minuses. Okay, so as defined it here, the attraction between a partially positive side of a molecule, the partially negative side of another molecule. Doesn't have to be the same molecule, it often is, but it could be two different molecules interacting, or it could be two molecules of the same compound. Okay, a little bit different than hydrogen bonding. So hydrogen bonding is actually a sharing of electron. It involves orbitals, and as such, the orbitals have to line up. A good thing to remember, if you remember that hydrogen bonding can occur when you have an H on an N, an O, or an F, then on your hydrogen bonding exam, you will get no F because you know it. So lone pairs on these three elements are free to interact with an H on one of these three elements. I'm going to regret doing this. And you notice I completely disregarded the Honk rule. I'm just focusing on this one. One thing I regret doing, and basically it's because I was cramped for space, it doesn't bend like that. So I need to rewrite this to be a little more specific. It should be in a straight line. So the covalent bond of the N to the H must be in a straight line so the orbitals overlap correctly. Probably best if I would have drawn it straight up. The O is a little bit better, not much, but I made a mistake when I draw it, is the dashed line doesn't look very dashed. So I'm going to redo that, emphasize it. So I was lazy to begin with, and I want this to be kind of a lesson in general. Do things the right way and you'll understand it much, much better. So a dashed line coming up to an H with a delta plus because it's bonded to an oxygen. So that represents a covalent bond right here. The dashed line represents the hydrogen bond. Notice the hydrogen bond is longer than the covalent bond because the covalent bond is stronger. And last, let me get rid of this really ugly one I did. And again, I want to draw it in a straight line. So it's going to come up from this lone pair onto an H, and that can go to an F. Now, I've drawn an N lone pair going to an H on an N O lone pair going to an H on an O, and an F lone pair going to an H on an F. But you have all the different combinations. So 3 donors, 3 receivers, 3 times 3 means there's 9 possibilities. The N lone pair can go to an H on an N, H on an O, or H on an F. The lone pair on an O can go H on an N, H on an O, or H on an F. Lone pair on an F could go to an H on an N, H on an O, or H on an F. So I've only drawn 3 of the 9 possibilities, something to hang on to thought-wise. Okay, I'm going to erase this. And again, want to emphasize, because it's an orbital overlap phenomenon, you have to have things line up the right way. But note that it's O, N, or F. No F. And then London dispersion forces, it's got a definite definition, and that would be an interaction of a dipole, but a dipole that's there temporarily. So in real life, you've experienced something like this when you took iron filings and put it near a magnet. So iron by itself is not magnetic. It's defined as something ferromagnetic, but it doesn't by itself exist in a magnetic state. You have to induce it. So you induce it in a couple of different ways. Magnetite is one where you actually mix it in with a doped metal. Let's say you toss in manganese or chromium or something like that, oxidize it slightly, and then heat it up to a certain temperature called the Curie temperature, let it cool, and it'll crystallize into a magnet. Ta-da, you got a magnet. But it needs the oxygen radicals and it needs the doping of the other metals in there to work. Iron naturally, although it has unpaired electrons, won't have them all line up in a way where you have magnetism. However, as soon as you put a magnetic field around it, they will align and take on a magnetic nature. London dispersion forces are kind of the same, except it's not magnetism we're talking about. It's electrostatics, meaning it's charge-based, not magnetism-based. And so for a brief moment, if you have a molecule, then when it passes by a plus charge, electrons move towards a plus, creating a delta minus for a brief moment. And on the other side, you have a delta plus. Just for that brief moment in time, it's got a temporary dipole, which means it will interact. So as 2 things pass, they might be attracted. And as they pull away, the attraction will go away. But it's still, on time average, there is some interaction. So I'm going to refer to it as a temporary partial charge, interacting with a temporary partial negative charge. But reality is, because it's temporary, it's not a very strong force. So as far as the ranking goes, hydrogen bonding is our strongest force, number 1. Dipole interactions, number 2. London dispersion are number 3. That said, London dispersion always exists because things can temporarily have charge induction. Dipole only exists when you have a difference in electronegativity between 2 atoms. The more drastic the difference, the bigger the dipole. And hydrogen bonding only exists with an NO and F. So LDFs, London dispersion forces, always exist. So generally, this molecule gets longer and longer. It has different spots that can interact with a neighboring molecule and can pack together in a way. That's what's going to impact solubility, melting point, and a few other factors. But the more that they interact, the more London dispersion forces. Okay, so we have our definitions. Examples. Dipole-dipole interaction. This is a molecule known as acetone, CH3, carbon with 3 H's bonded to another carbon, so 4 bonds of the carbon. Same thing with this CH3, this carbon here, 2 bonds of carbon and bond O. Mentioned briefly last lecture, has a dipole moment because O is more electronegative than carbon. Plus, with pi bonds, for whatever reason, they can move over more. You can relocate pi electron density more than sigma. So this can take on a delta plus and a delta minus. So this is going to be my delta minus. This is going to be my delta plus. This is going to become incredibly significant towards the end of this semester, because all of chemistry, all of organic chemistry, if you really whittle it down to the simplest thought, delta plus is going to interact with delta minus. Intermolecular forces in one case, or possibly a reaction. So in some cases, it might be a full minus that can come in and interact with this delta plus and form an actual covalent bond. Or it might be this delta minus, which interacts with something and coordinates so that the molecules line the right way to react. Meaning this delta plus, delta minus, as long as you can figure out where the pluses and minuses are, you'll be surprised how much chemistry you can predict. Okay, hydrogen bonding. This one also has a dipole. This is known as urea. So I should probably make it a habit of writing names in, because the more names we have, the more information we feel we can store. Acetone, urea. Urea is probably well known from your biointeractions. It's a major part of kidney filtration. You create a urea concentration gradient in your Bowman capsule, and this allows water to be reabsorbed. That'll be something that shows up in physiology, but it is a fairly important chemical. One note is it actually, although it looks like it should be more polar because you have some more electronegative atoms here than acetone, it actually isn't. So what happens here, oxygen pulls up this way, these carbons can help out a little bit. These nitrogens being more electronegative will actually hold on to their density a little bit more. We're going to learn about something called resonance that will share electron density as well. But for now, the polarity of this is just slightly different than the acetone. But what it can do is it has 1, 2, 3, 4 lone pairs on N and H on an N, H on an N, H on an N, H on N. So 4 nitrogens, or excuse me, 4 hydrogens on nitrogen, 4 lone pairs, meaning this thing in theory could have 1, 2, 3, 4 or hydrogen bonds because of lone pairs, 1, 2, 3, 4 because of H's. It is the most H bonding molecule we know of next to water. So where will pop up in your future is, sorry for the spoiler alert here, but our proteins are held together by a significant number of hydrogen bonds, so-called backbone of the DNA or the protein strand, sometimes side chain. But if you add urea to a protein rather than hydrogen bonding with itself, would rather hydrogen bond with urea because urea makes much stronger hydrogen bonds. So adding urea will actually start to denature or unravel protein structure. It'll stretch it out instead of a coiled system of whatever it normally exists in its natural state. It'll become unnatural. It'll become denatured, stretch out with a bunch of ureas on it. So I'll hang on to that for the future, but lots of H bonds. London dispersion forces. So I want to try to keep the central theme of a carbon-carbon in the middle with a double bond, carbon, nitrogen, nitrogen, carbon with a double bond, carbon, 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 carbon in the middle, double bond. The difference here, instead of electronegative atom like O, this one isn't very electronegative. So there is no dipole moment in this. If there is one, it's minuscule. But it can have temporary dipoles because electrons can move around, like I mentioned, pi bonds. We can put a delta minus here and a delta plus here temporarily. So if it's in the neighborhood of something positive, electrons will have a tendency to move over here and give it a delta minus temporarily. So you get very weak interactions because it's just a temporary force, not permanent. So let me get rid of everything I wrote in yellow. Bad planning on my part, but you have a delta plus, delta minus. Delta plus, delta minus, not as significant, but you have no delta plus, delta minus. Okay, gonna jump ahead of myself a little bit and talk about what's known as intermolecular forces applied to physical properties. So physical properties in this case represent things like the melting point and boiling point. If a molecule is held together very tightly, it takes a lot of energy to pull the molecules apart. This melting point, negative 94.6, just not that significant. Very, very low temperature, acetone is just not going to freeze. But acetone boils at 56, meaning acetone is naturally liquid. You may have used it as a solvent to remove, let's say, nail polish. May have used it as a solvent to remove like glue residue. It's good at dissolving things, but if it's ever spilled on yourself, it feels very, very cold. Even though it's at room temperature, it boils at such a low temperature that when it touches your skin, it can start sucking heat out of your way, or out of your skin, excuse me. And along the way, when it takes heat, drain heat from you, you feel a little bit on the cold side. So I don't know if you've ever done this, spilled acetone on yourself, but even though acetone is at room temperature, it feels cold because when it evaporates away, it takes heat. It's an endothermic process. But the point here, it's a liquid, but with a relatively low boiling point. Urea, we know hydrogen bonding is the strongest of the interactions. So because this is the strongest interaction, hydrogen bonding, we expect molecules to be held together more tightly. So urea could have a much higher melting point and boiling point. And in fact, because it's a solid room temperature, I know the melting point is over 25, 26, 27, whatever room temperature is said to be, but this one has an extremely high melting point. So just like water, for as light as it is, you'd expect it to have a very low melting point, but it's relatively high. Melting point is 0, and the boiling point is extremely high at 100. This is for water. Urea, even higher because it has even stronger hydrogen bonding and is a little bit heavier. So the one piece of the puzzle that I want to emphasize, these all have roughly the same molecular mass. And the reason I did that is because how high the boiling point or melting point are does depend especially the boiling point, on the weight of a compound. The heavier the compound is, the more energy it takes to quote unquote lift it out of its solution. So heavier things have higher boiling points, but these are all roughly comparable. So 6 H's, 4 H's, 8 H's. O is slightly heavier than carbon. So 3 carbons and an O, 3 carbons or 4 carbons, and carbon, O, and 2 N's. 14, 12, and 16. So the weights, I'm just hand waving this, but the weights are all really, really close. So the extra 2 H's are offset in this case by N being a little heavier than carbon. And this one's offset a little bit because carbon's lighter than O, but the 2 extra H's. So the weights are close. That's, I guess, my point, babbling on. Then finally, London dispersion forces are the weakest. So we see the lowest boiling point and lowest melting point. So the weakest forces means this turns into a gas very easily. This one turns into a solid and a liquid, or solid and gas, excuse me, easily a solid, hard to turn into a liquid or gas. This one's easily a gas, I should have said down here, and this one comes as a liquid. So let me write that in. Emphasize that this is liquid because it has the medium forces. This is a solid because it has the strongest forces. And this is a gas because it has the weakest forces. Hopefully it seems okay. I got a little lost in the middle there, so hopefully it makes sense. So let me just clarify this. Strong forces, H bond is the strongest, held together most tightly, so it takes a lot of energy to pull the molecule apart, to pull molecules apart from one another, I should say. So melting point is high, boiling point is high. This one is a middle range forces, so it's a liquid because boiling point is 56, room temperature is, let's say, 25, but it has melted, so they're not completely pulled apart, but they are weakened. And then very weak forces, so this pulls away, the molecules pull away from one another, it's easy to make it boil. So at room temperature, 25 degrees, much higher than negative 6.9, this will be a gas. So the hope here is that this concept of how strong the forces are makes sense. This is in terms of physical properties, which we will address towards the tail end of this lecture, but just wanted to toss them out there. So as mentioned, H bonds will occur. So let me just double check. We have an H on an O, H on an O. We have some lone pairs. But the problem is they're not lined up. This is way too far from that lone pair there. That lone pair is too far away from that one. So the molecules have to rotate, get close together. So let's see how they do this. Oh, there they are tumbling around. And they will rotate around, they'll move, they'll do whatever they do in solution until you get just the right lineup where this covalent bond is in a straight line with the H to lone pair. So the minute that lines up, this lone pair's orbital is aligned correctly to attack the H. So we end up with that covalent bond lined up perfectly with the H bond. Absolutely positively critical that you note that it's an orbital overlap because that causes this to be lined up a specific way. And in OChem, I'm not going to care that much about it. But when you get into biochem, molecular biology, that becomes incredibly important because proteins have to line up a certain way to get their hydrogen bonds, DNA, RNAs. Their bases have to line up a certain way to get the right H bond alignment. Consequently, they take on very specific structures. So I'm sure you heard of like an alpha helix before, and a protein exists because H bond has to be lined up a certain way, so the protein has to fold a certain way. In DNA, the base pairing, you know how it goes. So if you know that AT and CG go together, it's because those are the ones that have the right lineup. You can't really put an A with a G or a C with a T very easily because although it will H bond, it doesn't H bond as tightly in correct alignment as the pairs. So much bigger thing when you get into bio, but still useful for OChem. So if I consider these urea molecules, so here's my NH2, NH2 on a carbonyl, NH2, NH2 on carbonyl. Because this is lined up, that can hydrogen bond, that's lined up so that can hydrogen bond. I'm going to get those two. In this network, if it lines up again, this O might be able to line up in somewhere, this one might be able to line up. This H can line up with something, this can line up with something. So it starts getting this massive network. So if there's some molecule there, it can line up. So we start recognizing all the ways this line up. So I only focus on these two initially because that's the way it's lined up. But if another urea kicks in there, another urea, it becomes a pretty strong lattice network. So it's a trigonal planar molecule because of what we'll learn is resonance down the road, but it's able to pack into this nice crystalline structure because of so many H bonds. So bio spoiler alert. Okay, urea, as I mentioned, is added to denature proteins. So I alluded to something. Let me make sure we know what a protein is exactly. So protein is a long strand of amino acids, which have an amine group, an alpha carbon, carbonyl carbon, connected to an amine, an alpha carbon, and a carbonyl, check, connected to an amine, an alpha carbon, carbonyl, check, connected to, I see the trend here, N, alpha carbon, carbonyl, N, alpha carbon, carbonyl, and so forth. So I'm just going to stay with it. But notice at the end, it's an acid here, and it's amine here. Hence the term amino acid. But this long chain of this protein. So this represents 1, 2, 3, 4, 5, 6 amino acids strung together in what's called a peptide bond, as you'll learn in bio. So you have this long protein strand. Here you have a completely different protein strand. So here's my amine, alpha carbon, carbonyl, amine, alpha carbon, carbonyl, and so forth. They don't line up as perfect as they can as I've drawn it here, because I tried to make them all planar. So it ends up, for this to line up the right way, this will have to pucker in, this will have to pucker down a little bit, pucker down right here, pucker in a little bit. And so if it does that, you can get it to line up a little bit better, and you force it into a certain structure, which in this case, I've tried to represent something called a beta pleated sheet. You may have learned that at some point in your bio travels. You may have also heard of something called an alpha helix, where it coils within itself, hydrogen bonds with its own strand. So these become really important features. Okay, I'm going to get rid of this because, as I mentioned, urea is a better H bonder. So you're this protein, and you have a nice H bond here. It's not lined up perfectly straight, so it's not maybe as strong as it could be, but it's still pretty good. But what if urea came along, and instead of forming this kind of weak H bond, you could form a stronger one, you'd leave here and you'd leave there, start breaking that bond, breaking that bond, breaking that bond. So any of the hydrogen bonding in that protein network is going to go away, and you'll end up with something like this. So urea is going to form stronger H bonds than protein, which causes the protein to unravel. So a little more complex, but that single strand I had, so here's my protein from before. Here's the first amino acid, second amino acid, third, fourth, fifth, and sixth. My amino acids, the same thing, the strand, but it's now, instead of being hydrogen bonded, I've drawn it at the same angles, but this is now free to rotate and become a straighter, stronger H bond. This is now free to rotate, become a stronger, straighter H bond. Rotate. So it can form a stronger H bond. So I'm going to leave it like this to emphasize this is how it would line up with the protein. When it lines up in a better way, you have an even stronger H bond. So therefore, this protein would rather have a whole bunch of urea on it. So again, urea is a denaturing agent. So a lot of times when you do things in biochemistry, if you're doing an experiment where you want to sequence, determine what amino acids are in a protein, you have to first denature it, get it out of its coiled natural state. So a lot of times you'll add 2 molar urea to denature it, to make it this long strand. So now I can do a reaction on just that amino acid without the coiling of the amino acid getting in the way. So that's your biochem spoiler. That means next semester when you take biochemistry, you can just totally sleep through this 10 minutes of lecture because you already totally know it. Just kidding, please don't. So RNA and DNA also mentioned that they base pair in a very specific fashion. So mentioned, I said A and T, but I'm going to go with A and U. And the difference is pretty much just a CH3 group between a T and a U. And that's also the fun, like RNA and DNA differ in one of the, one of the OHs on the backbone. Deoxy means this has one less O. RNA has one more O on the sugar backbone. So I don't know what I've drawn here, so I'm going to quickly double check it. This is called the sugar, has an O here, check, has an equivalent of an O. The base replaced an O, has an O at that one. Kethane has an O in the phosphate on carbon 3, has an O here. So this isn't deoxy, this has the oxygen there. So this must be RNA. So uracil, that should have also given away. So this, I've drawn an RNA. I could have easily, if I wanted to, drawn a DNA. Guanine and cytosine, same sort of thing. So I want to emphasize these line up just the right way. So A pairs with C or A pairs with T, depending on RNA or DNA. G pairs with C, because they line up just right to get 3 H bonds. Absolutely imperative. So if I tried to line up A with C, may not work as well. U with G, it could happen, don't get me wrong, but it won't be the most stable thing. In our body, eventually things become more stable. Okay, so the H bond is highly directional, forcing RNA and DNA to bend into place. Hopefully that makes sense, but that's why I've drawn tilted. So this structure is bent over, emphasizing the H bonds have to be lined up straight. There are your bio alerts. So I mentioned a few things along the way. So I want to go ahead and apply this to a few questions. In this particular class, I'm going to worry a lot about melting points and boiling points. I'm also going to care a little bit about solubility, but let's go with this one in terms of boiling points. So boiling point is a physical property you can predict out of behavior of a compound. So I'm going to get way ahead of myself. I'm actually going to start teaching things that you won't get till later on in this semester, but you did cover it really briefly in 121 lab. And that was the IR, when you looked at an alcohol, was very broad because it was an OH interacting through H bonding. So this is kind of narrow. So this is a little bit of H bonding. This is a little bit wider, more H bonding. This one's really wide. So this is a lot of H bonding. So this is little H bonds. This is lots of, very scientific word, lots of H bonding going on. Okay, so the relative boiling point. So the boiling point is going to depend on two things: molecular weight and intermolecular forces, IMFs. Intermolecular forces, we know H bonding is the strongest, followed by polarity, followed by London dispersion forces. So if you have H bonding, you're going to win. Molecular weight, C7H14O, C7H14O, and C7H14O, they all have the exact same molecular weight. So it cannot be a difference in molecular weight. So the greatest boiling point has nothing to do with molecular weight. So I should be able to get rid of choice C right away. Okay, next on the agenda. Most polar, least polar doesn't matter as much as H bonding. So I'm going to say this one doesn't matter because even if it is a least polar, which I don't know for sure, I know least polar wouldn't make it the highest boiling point. Least polar, weaker than molecular forces, is counterintuitive to what it should be. So if they're all polar, that's fine. Least polar would be lowest boiling point, not highest. So that's out. Down to two choices. Trusting that this is a narrow peak, little H bond, this is a wide peak, lots of H bonds. Compound 3 has the greatest intermolecular H bonding because of the broadness. So it must have the highest boiling point. More H bonding, higher boiling point. This is a really tough question. I do not expect anybody in class to get this right away. But this is a case where every now and then when you get a question and you get it wrong, that is completely okay because you learn from it. So I'm going to call this a learning question. I would assume if you got it right, there's a high probability you might have used a little random guessing. If you did recognize the width of the peak corresponding to H bonding, that's excellent. That's where I want to go with this. So eventually we'll get into that point, but challenging question to recognize how much H bonding. That's the hard part. But at the very least, you should note they're all the same molecular weight. So any difference in boiling point can only be attributed to intermolecular forces. Least polar would have been lowest. So that one you should have got rid of. And C you should have got rid of. But deciding between these two, that's really challenging. Okay. So B is your best answer here. Solubility and miscibility. Kind of anal to make a big deal about the difference in definitions, but I still will. Solubility is the ability of a compound to go into a solution where it's going to a solvent that is naturally in a different phase. Miscibility is where it goes into a solvent that is the same phase. So oil and water are immiscible because they're both liquids, but one liquid doesn't go into the other. Salt is insoluble in oil because salt's a solid, oil's a liquid, doesn't go in, so we refer to it as solubility. Subtle difference. I'm going to be really, uptight about making sure you don't make that mistake in terminology. Probably isn't as big a deal as I'm making out of it, but that's your fundamental difference. So solubility, the dissolving of a solid or a gas into a liquid, that's how we're going to use it. So that isn't necessarily the only definition. Something like a solid evaporating way into the atmosphere is technically solubility. It's dissolving into the air, which is a solvent, a fluid. But for us, we're just going to consider solid or gas molecules going into a liquid. In chemistry, the solvent is the one that's going to change everything. So it can be polar or non-polar. So solubility, if you have a polar compound going to polar solvent, it's going to be highly soluble. If you have a non-polar compound going into a polar solvent, it's generally going to be insoluble. So that's going to be something we're going to look at when you do lab. Miscibility, the mixing of a liquid into another liquid. Like solubility, it's the same thing, except solute and solvent are in the same phase. When they're immiscible, you have the less dense one floating on the more dense one. Random fact. Like dissolves like. Need you to memorize that thought. Be careful not blindly apply it. But if you have two molecules in roughly equal concentration, they will mix in with one another if they have like properties. Polar will dissolve into polar. Aprotic will dissolve into aprotic. You'll have similar solubility rules. Okay, so water lipid immiscibility. One hydrogen bond and is polar. The other one is non-polar, only has London dispersion forces. So therefore, they become relatively insoluble. So we use this for waterproofing. Really awesome example. If you've ever seen, like in the wintertime, geese, you see them flying along, they'll always land in that frozen lake or frozen pond or the river that's barely moving but has ice built up on it. They do that because they actually start to overheat in the winter because they release a large amount of oil, a large amount of wax on their feathers. So by putting all this wax, all this oil on their skin, on their feathers, on their exterior, the water can't seep in. The cold water can't get into them. So they're able to trap their heat in, and therefore they need the cold water to suck the heat out. So when they fly, they have all that heat trapped in because it just can't escape as easily. It's also why, if you ever see people who swim long distances, like they swim from one island to the shore of the land nearby or whatever they might do, a lot of times they'll wax themselves up for that same reason. So a few natural occurring compounds, long alkyl chains. So 1 plus 14, 15 carbons long. You have a carbonyl and a oxygen in here. It's going to be called an ester. We'll write the name. And then on the other end, you have 15 plus 1, 16. So 15 carbons, an ester, and 16 carbons. Lots and lots and lots of carbons. So it's large enough that it gets so heavy that it can't really easily melt. But waxes are very malleable. So you can pack them together, move them around. We use them for structural materials that can be quickly built and quickly broken down. So on a lot of candies and pills, you have the same sort of thing, a little bit longer wax, so it's a little bit harder. Beeswax is kind of soft. The coating on candies or let's say whatever medicine they have, it breaks down. You can hydrolyze it. It can cleave in the stomach, but it's still a long alkyl chain, 25 carbons here, plus a carbonyl, and then 20 carbons here. Finally, cannula wax, just even longer chains. Longer the chains, the more solid it becomes. So a lot of times you have this car coating, or the wax you put on a car coating, for instance, just stays on there. It crystallizes out, forms this layer. Water can't penetrate it. So if you've ever seen water bead up on your car when it's waxed, that little water bead is because it doesn't interact. You ever see it like a duck or goose or whatever in the lake in the wintertime? They don't get too terribly cold from the water because the water can't seep through. Why do we have earwax? Same thing, we're waterproofed. Okay, So wax is typically esters made from two very long carbon chains. That's the point I'm trying to make. And these things become, I think, kind of interesting. So hopefully it works out well. In case you're watching this lecture before the very first lecture, I'm going to ignore the obvious that we discussed the wax during that time. Okay, so known as amphipathic. So amphipathic molecules are ones that don't know what they are. They're polar and ionic at one end, and they're non-polar at the other. So amphi meaning both, pathic, both solubility. So this could potentially dissolve into oil, but this wants to dissolve into water. So where these become useful, you have a hydrophobic tail, meaning it fears water. It doesn't want to dissolve into water. It wants to be in a lipid or oil environment. Up here we have the ionic head, wants to interact with water. So if we have a layer of water, and I've chosen this carboxylate will want to go into the water. That negative charge wants to be in the water layer, but this alkyl layer will be over here. So you end up getting this biphasic system. So if you've ever added soap to water, you'll notice a little soap film on the top. That's this tail not wanting to go into the water. Eventually, it will go into the water. If you agitate it enough, we'll talk about what's known as a micelle in a second. But the aggregated hydrophobic tails in this water. You have probably also seen this in terms of cell membranes. So we'll go into cell membranes as well, but this is a cell wall alignment because you only have a single lipid, but a lipid bilayer. If I had another lipid up here, another carboxyl or carboxylate or phosphate or whatever negative charge I want, that'd be simulating a cell membrane a little bit more. So ionic heads go into water, aggregate hydrophobic tails stay out of the water. Detergents work this way. So detergents, very similar. So when it's a carboxylic acid group or carboxylate, we call it a soap. When it's a sulfate or phosphate, we call it a detergent. Don't ask me why somebody decided that this is important to know these different terms, but that's how they distinguish one from the other. They have the same basic approach, hydrophobic end to pick up oil. So let's say you have an oil stain on your clothing. The oil can start attracting to this part, but then this part can be sucked into the water. So when I wash it away, this will get sucked into the water and pull it, taking this tail with it and dragging along the oil or the dirt. So detergents help to bind an oil or bind a lipid molecule and drag it into a water-soluble environment. So I'm tossing a bunch of these out here. These are just different ways we get positives. A positive in a protonated amine or a four-bonded nitrogen, a sulfate, a phosphate, a carboxylate. Lots of different ways, but all are basically the same fundamental idea here. I don't know if you really need to know the terminology, but if you're interested, sodium, positive charge, para means it's substituted apart from one another. Dodecyl is 12, so if you counted, you should get 12 carbons coming up to this ring. Benzene is this, sulfonate is when it has a negative charge, we call it an 8, or a negative with an O. So the nomenclature hopefully makes some sense. Not responsible for that nomenclature yet. So, mention something that happens with soaps called micelle formation. Micelle formation is going to make it simple where this is the polar head. I don't care which of the things we talked about. So it could be a carboxylate group, but it also could have been the sulfate, the phosphate, the ammonium, the positive charge. I don't really care. And then the alkyl tail. Mention its odd number. That is completely irrelevant, but I want to bring up why I'd even bother putting that in there. Naturally occurring fats, as you perhaps learned in your bio courses, typically come from acetyl-CoA, a 2-carbon species. So when you build fats, it's 2 plus 2 plus another 2 plus another 2 plus another 2. So it's very common that your naturally occurring fats are 12 carbons, 14 carbons, 16 carbons, 18, 20, etc., where the last carbon is a carboxylate. So by emphasizing that this is an odd number, I'm trying to say subtly, this is a naturally occurring fat that could, or an amphipathic molecule, but a naturally occurring lipid that can form a natural micelle in your body. So like attracts like dissolves like. So if I'm in a water environment, the polar head will want to interact with water. So I've just drawn this as a 2-dimensional circle, but reality, it's actually 3-dimensional. So there's some coming up towards me, some going in, but I want to emphasize this. Plus, I think it's just so cool to look at that, I guess, sort of implied circle right there. What we have is the following. We have all these polar heads, which means this blob is highly soluble in water, but it forms like an inside-out bubble where the inside is hydrophobic. So again, if you toss this into a tank of water, like a dishwasher or washing machine, something like that, this micelle will form, and it will allow a nonpolar molecule to migrate into the core and carry it out. So it's like a little shuttle, little craft to move that molecule out. So if I put a lipid molecule in here, let's say lipid molecule fit right there, this whole micelle can dissolve in water and shuttle it away. So soaps work in the following way by making the so-called micelle. So the polar heads are attracted to water. The hydrophilic tails want to get away from the water, so they all aggregate in the middle. Now, I want you to look at this and tell me what the heck this could be. So think about it for a second, what the difference is. So I've changed the molecule on you slightly, and it's doing something a little bit different. So here's this part: polar head, hydrophobic tail, polar head, hydrophobic tail, polar head, hydrophobic tail. That's all fine. But notice I have another one here. So really, if I was really careful and looked at it, I have one group there and another group here. I have one group here, another group here. So they're bunched together that way. So it's almost like you have a micelle that for some reason had a second micelle on the inside that created this pocket. So I have a water-friendly environment out here, but I also have a water pocket in here. And then the surrounding is the lipid bilayer through there. You have seen this in your biology classes. And again, I'm drawing this in 2 dimensions. You have to realize these are all done in 3 dimensions. But a lot of times in bio, we'll look at a freeze fracture, we'll crack it and just look at one cross section. So this is essentially like that, just one cross section of whatever cell we're looking at. But this is the outer ring here, this inner ring here, and it's just back to back. So if I take one of these molecules here and line it up like this, and then take another one, line up like that, and another one, line up like that, and I keep on doing that around and around and around and around and around and around and around, I will get this micelle. Micelles, I'm sorry, this phospholipid bilayer. It's a glorified micelle, and just one note, this is something for bio classes, but depending on what concentration you put in, how much you agitate it, it will pick its optimal size micelle. The ratio of what the environment is, the amount of lipid, the amount of water, the amount of agitation will lead to this. But if you put this soap into water and leave it long enough, you'll get a micelle. Agitate it the right way, and you can eventually get a cell, the equivalent of a cell membrane. So I hope this picture makes sense, what these two are. This is, I think, just an interesting thing. I'm going to say it's probably beyond the scope and target of this course, but this is why OCHEM is so absolutely critical. So if everybody's taken cell bio so far, you know all about the cell membrane, and you'll know that, oh wait, we can also put things in here like protein channels. So proteins also have hydrophilic and hydrophobic groups. You have a bunch of hydrophobic groups there, make a hydrophilic channel so ions can go in and out of it. You can also put transporter molecules into here. They can do a reaction, shuttle the molecule in, and unreact it so it can go in. Lots and lots of bio is rooted in understanding very fundamental chemistry. The fundamental thing here, like dissolves like. Ionic compounds, like water, so water dissolves ionic compounds. Like dissolves like, lipid aggregates with lipid, so the lipid part of the protein dissolves into the lipid bilayer, and the hydrophilic part is out here, so it's the core of the channel. Okay, want to apply it to a couple real-life situations. Cholesterol is a very common molecule in our body. It's a precursor to pretty much every steroid-based hormone we have. And again, I haven't gone into enough detail to explain what this drawing is, but I'm sure you've seen drawings like this when you took bio. where this represents, every point represents a carbon. So here's a carbon. It has an OH, bond to carbon, so it must have another H there. This is a carbon with a bond to carbon, so it has two H's. You can figure it out. So we'll get into this type of drawing a little bit more in the future lectures. But just trust this is a long carbon, or set of carbon rings and a long carbon chain with just one tiny little OH. So this molecule, troublesome in the body. We desperately need it because it incorporates into our cell membranes. When we modify it to turn into other steroid-based molecules, those also incorporate into our cell membrane. They send a message, but this can incorporate in, this part can send a message, or this can incorporate in, and this part can send a message. All depends on what exactly it's doing, but we will say this is a very common precursor and a very common molecule to affect my cell membrane fluidity. Getting it through the body is really tough to do because it is highly hydrophobic with just a tiny bit of OH. Folic acid, that's what happens after you're done with cholesterol. You break it down. When you break it down and it's ready to be discarded from the body, this OH is still here. This pi bond is gone. You oxidize here. So you oxidize at the so-called alpha position to here. We'll mention why that is again in later lectures. You put an OH here, and you oxidize this in, cleave this thing off, turn it into a carboxylic acid. This only has one OH. This is highly insoluble in water, whereas this compound has 1, 2, 3, 4 groups. So its desire to pick up water is much greater. It still has a hydrophilic core, but hydrophobic ends. So if this molecule starts aggregating together, it's going to be kind of cool because it'll stack together pretty nicely. It'll have all these water-loving pieces. So you get a chunk of this material with these water-soluble pieces. And again, this is probably too much information, but this ends up being discharged from our body. When we break down cholesterol, this is how we discharge it, cholate. It travels through the colon. I don't think that's where the name comes from, but I'm going to just assume it's somewhat similar to that. But cholate, when this is deprotonated, it'll pass through our body. Water will bind it. So if you're constipated, you don't have enough water bound to the edges of this. It doesn't go through very easily. If you have enough water, you don't get constipated. It hangs onto this. So this is a component of our waste. This allows us to take out lipid waste. So you probably haven't really thought about this, but when you urinate, it's water-based. So that's how we get rid of our salts, our water-soluble metabolites and impurities. But if you take in your diet with a lot of lipids, a lot of oils, you can't put them into water base, so you can't urinate them out. So you have to actually discard them through solid waste. And again, way too much information and probably borderline bio and definitely borderline disgusting. But they say, doctors will tell you, you should monitor your waste. The color of your urine is important, tells you how much concentration you have of impurities in there. It tells you whether you're hydrated or dehydrated. So does the fact you're thirsty, but that's one way to monitor it. But also, when you release waste, how much oil floats, how much, like the density of it is, way too much information. I'm overthinking this, but you can make a good approximation of exactly what percentages you have of water, this compound, and the rest of waste. Just food for thought. So I've taken the lipid versus water situation a little far, but as long as I'm doing that, one of these things, just a thought experiment you should do is trace anything you consume. So let's say you have a piece of bread. You take it in orally initially. Salivary amylase is going to help break it down. Water in your mouth is going to help cleave those bonds. You get very dehydrated when you take in starches like that, but you break it from a macromolecule into smaller oligo, still macro, but a little bit smaller chunks, go into your stomach, where you now start breaking it down with acidic water, cleave it down a little bit more, passes through the pyloric sphincter into the small intestine, where you end up breaking it down now with pancreatic amylase. Amylase just breaks down the sugar, so we break it down more and more and more. And then that sugar molecule, that glucose molecule, is going to have to travel through your bloodstream, which will be able to do because it has a lot of OH group, so it has a lot of H bonding. But then to get it into the cell, to actually take it into your cell and use it, it has to pass through the cell membrane. Because it's so water-loving, it cannot pass through the cell membrane without some assistance. So if you think about anything that you've taken orally that ends up in your cell, it has to get help getting across the cell membrane. It's going to be fine in the water-based area, like our stomach, our intestines, our blood, but it can't cross the cell membrane without having a transporter or carrier molecule of some sort. Conversely, let's say you've ever taken vitamin E. You have that little gelatin pill. When you take that vitamin E, it's actually a lot of soap in there. Sorry, I'm not good in the marketing here because you probably don't want to take vitamin E now, but if you do, those lipids, the little soap you put in there, will aggregate into a micelle. That micelle will actually take the lipid molecule, the vitamin E structure, the actual vitamin E molecule in its core. That will now travel peacefully through the water-based area, your stomach, your intestine, your blood. But then when it gets to the cell membrane, it can turn inside out and deliver it into the cell membrane. So our lipid-soluble drugs actually don't go into our cells. They act within the cell membrane most often. So kind of cool when you think about where things end up. So from oral ingestion to how it ends up in your cell, it's one way or another going to have an unfriendly neighborhood. If it's water-loving, hydrophilic, it's going to be perfect until it has to traverse across the cell membrane. If it's lipophilic, it doesn't like water, then it has to have a micelle to transport it through the water area, and then naturally will incorporate into the cell membrane. Now to get it out, when you have all these wastes, same sort of story. This molecule is going to help to facilitate movement of lipid waste. So I've gone way too much into bio, but I hope that's sort of an interesting tangent. A couple of practice questions. So nothing like the positive attitude. They aren't practice questions. They're your happy chance to show off everything you know. So happy time. Conversion of cholesterol into nucleic acid involves. So if I go back to what it was, I remember it had one OH and it finished with 4. So it had to pick up oxygens. So from here to here, I have no idea because we're not talking about this. So I've just thrown a real hard question at you that I want you to use your intuition and knowledge. You gained oxygen. Keep things as simple as this. So all the way back to the first lecture, we said, when you come to a question, look at it simply as you can. Are we substituting anything on here? Is there something coming off, something going on? I don't know. Electrocyclic, the word cyclic means we make a ring. Well, we have 1, 2, 3, 4 rings going to 1, 2, 3, 4 rings. We didn't make any rings, but we did oxidize it. It gained bonds to O. We did not reduce it. It did not gain bonds to H and lose O's. So best answer, it's not substituting, it's not forming new rings, and it's been oxidized rather than reduced. So the best answer, C, is in cool. Why do I throw this question, which is a bio question with an OChem twist that talks about a reaction we won't get till second semester and a reaction we won't get until chapter 7? And something that's, you got a little bit in GChem, you're going to get more in chapter 12 and 19 this semester, you're going to get it in biochem, you're going to see this a lot. So why would I do that? My hope is this, is that as we're learning OChem, don't treat it as its own subject. Treat it as tools to understand other subjects. The bio examples in this lecture, I love because it enriches your understanding of OChem, knowing why I care about hydrophilic and hydrophobic, lipid and aqueous, protic and aprotic. All these words I kept throwing at you, some are chem words, some are biochem words, some are bio words. They're all saying the same thing. We teach the same thing over and over in different sciences using different terminology. Your job, when you see something like this is really a physiology, a biochem, or an OChem topic. It could be any of the three. See the big picture. Okay, what is the role of an LDL, so-called low-density lipoprotein? Okay, this is again along the same line as cholesterol. Mentioned cholesterol is very hard to move through the body. It needs a micelle. A low-density lipoprotein, so lipo means lipid, an oil chain, and a protein, depending on what amino acids you have, can be polar, non-polar, can be hydrophilic, hydrophobic, all that. In this case, it is a hydrophilic protein and a lipid chain. So this is pretty much just like what we had earlier, an amphipathic molecule where the lipo chain, long chain, and the protein is a positive head, like the nitrogen with a positive charge, or carboxylate, just like the amino acid has a C terminal, N terminal. So it can form a micelle. I'm not going to make it nearly as pretty as the picture was earlier, but as it starts aggregating, and then that cholesterol molecule I haven't drawn it perfectly. There's a few other things going on here, but close enough. It can fit into the core of this micelle, and this micelle can now move through the bloodstream and drag it with it. So, as mentioned before, trace any molecule from oral consumption to how it interacts with the cell, and then from when it's released from the cell to how it's discarded through either urine or solid waste. If you do that, you'll find this topic to be pretty interesting, how things move around. But the whole purpose of low density lipoprotein doesn't help with the synthesis, doesn't oxidize, reduce anything, doesn't do any chemical reaction. It helps transport the lipid friendly molecule through the water friendly environment. So they don't do anything synthesis wise, they don't cause any sort of reaction. So you have to decide how does it help with transport. It takes an oil, a lipid, and helps it move through an aqueous environment, like dissolves like. Hopefully this, again, is a fun and interesting topic. So this is where I will end this one. So have an absolutely wonderful day, and I will see you in lecture or talk to you in the next one we get to. Thank you. Bye.